This is a demonstration of Mechatronics Concept Designer, the new end-to-end machine design solution from Siemens PLM software. We will trace the machine design process from requirements definition to the detailed machine using the example of a ring loader machine. We will start off by defining some requirements. This is standard Team Center functionality. It is not unique to Mechatronics Concept Designer. First, we open an existing requirement structure and drag it to the Requirements Manager. The requirement structure comes from a Word document and is based on the structure inside this document. This is important because so many machine makers use things like Word documents to track requirements right now, so it's easier for you to adapt your process to Mechatronics Concept Designer. The Word document is associative with this requirement, so if you change one, it changes the other. After we are done editing the existing requirement, we will create a new requirement, this one being for the maximum diameter of the gear. Now that we have defined some requirements, we will do the same thing for functions. We open an existing functional structure and drag our function to the structure editor. As we look at the detail of our handling units, notice that each handling unit is composed of a vertical motion and a gripper. The grippers have two variants, rotary and linear motion. These are denoted by the green V in a circle. We will then specify that we want to use the variant with linear motion, after which the rotary motion variants disappear from our structure. Once this is done, we drag both our requirement and our function to the Requirements Manager. This opens both the requirements and the functions and allows us to create links between them as needed. Functions define how the actual components will work to satisfy the customer requirements. We select the maximum diameter requirement and the gripper function and create a trace link between them. This link will be traced and used by Mechatronics Concept Designer. Now we can begin to create the physical geometry for our ring loader. We will open the functional structure that we just created in Team Center. Notice that there are two alternatives for this functional model using the rotary and linear grippers. After opening the functional model, we open up the structure to show the details contained within it. We can also create new requirements and links here, and they will be fully associative to the ones created in Team Center. At this point, we begin placing the geometry in the model that will help us implement the functions that we have defined. This illustrates how the physical machine design is always tied back to the customer requirements at all times. Now that we have placed some of the components of our ring loader, we can start the simulation. Notice that we can interact with the machine while the simulation is running. In this case, since we have not yet defined the physical links between the components, they are able to just move anywhere in the physical space. Our simulation also accounts for gravity, as you can see. This allows you to see what constraints you need to add to your model, but more importantly, it also shows you how your machine will act in a real-world environment so that you can adjust your design accordingly. Mechatronics Concept Designer uses simulation technology licensed from the video gaming industry. We further refine the design by adding various constraints, in this case hinge joints and sliding joints. These joints will tell Mechatronics Concept Designer how we want the various components to interact with each other, how they are allowed to move and not move. After adding the joints, we run the simulation again. Note that we are still able to grab the components and move them around, but they only move where the constraints allow them to move. To further refine our design, we begin adding position controls to the different components in our machine. These controls will be added to the sensor and actuator list, which is an essential data structure which enables the collaboration of the electrical and mechanical departments. We specify the position and speed for the components. In this case, we want them to stay still, so the speed we specify is 0. When we run the simulation again, the components that we applied the position controls to do not move. Now that we have placed these position controls, we can begin adding operations to the model to simulate the movement of the components. Notice that we have red arrow icons representing each of these motors, or places where an operation can be specified. The operations tell the system what speed and position to use for the movement of each component. Now when we run the simulation, the components move, although at this point all the movement happens at once. We can fix that by opening up the sequence editor. This shows the various operations in the form of a Gantt chart, which can be easily edited by dragging and dropping each operation to its proper place in the sequence. Now when we run the simulation, the operations happen in the proper order. These operations are examples of time-based behavior. In the last step, we specified the movement of our gripper part, but as you can see, it went up too high. In order to fix this, we need to put in a sensor to stop it. We will get one from the reuse library. Once we drag it into our model, we run the simulation again and see that the gripper is still moving up too much. We need to provide the system with more information so that it will act like we want it to. We open up the operation that moves the gripper up, and then we modify the speed parameter by making it conditional. The condition is that once the gripper comes in contact with the sensor, the speed becomes 0. In other words, it stops. Now when we run the simulation, the gripper stops when it makes contact with the sensor. This is an example of how you can add event-based behavior to your model. This is a rotary motion gripper component. It is an intelligent object. In other words, it has kinematic information built in. Intelligent objects in Mechatronics Concept Designer can have any kind of design data built in, mechanical, electrical, or automation. Taking a look at our ring loader again, you can see that all the motion is defined correctly and that both grippers now move and open as we want them to, with a linear motion. However, we wish to change one gripper to a rotary motion version like the one we just saw. After stopping the simulation, we delete the linear gripper from the machine. We then open the reuse library and drag our new rotary gripper into it. This intelligent object snaps to the correct location, but it does not know how to orient itself in relation to the rest of the machine. It does, however, know that it needs to open its grips when the simulation is started because of the intelligence built into it. Once we add a sliding joint and modify the sequence of operations in the sequence editor, the new gripper functions as we want it to. Up until now, we have been working with simplified CAD models of the components of our ring loader machine. This helps us illustrate the features of Mechatronics Concept Designer in an easy-to-understand way. However, once the basic design has been completed, we will swap out the simplified models for more detailed representations. Notice that the behavior of the model is exactly the same with the detailed models. The front gripper acts the same as the rear one. This carries over to the whole machine model, as you can now see the complete ring loader assembly model with accurate behavior modeling in Mechatronics Concept Designer. Mechatronics Concept Designer enables complete end-to-end machine design from requirements to a finished design. Its advanced simulation capabilities make it easy to define and validate the design of your machine before you start the costly mechanical, electrical, and software detailing, leading to higher quality designs in less time.